So hello everyone, this is the second example for the fins. So this example is about, this is again uniform, we are dealing with uniform fins, but you can also deal with the non-uniform fins. So this is an engine cylinder which has the aluminum alloy with 20-20-46, and these are the dimensions that are shown: 6 millimeters, which is the thickness of the fin, and the height of the cylinder is 150 millimeters, and we have the annular fins. The question is, find the increase in heat transfer due to added 6 fins. Okay, so we have 6 fins here, so it says that find added heat transfer, and the temperature at the base is 230 degrees Celsius. So we have here temperature of 230 degrees Celsius, and the environment temperature and the convective heat transfer coefficient is 25 degrees Celsius is the environment temperature, and the H of the environment is 60, and this H value is too high. So it means that there is at least wind blowing across it, or there are fans that blows air over the cylinder. So we have the fins here, you can see the annular fins here. So the number is different here, but anyway, it will give understanding how to calculate the fin. These are the fins. Cross section, you see it is 3D. You will have one more here, same here you will have at the back of it. Good, now let's start to calculate the increase of heat due to added fins. So firstly, this is about the effectiveness of the fins. We should identify 3 important areas for this one. So we will have area of the fin, you will have the area of unfinned parts. Area of the fin is clear, so we'll have the area of this fin. Area unfinned part is, you see these parts do not have any fin. So we should find the area of these unfinned parts, because heat transfer happens from the unfinned parts and as well as from the finned parts. Okay, so this is the finned area, top and the bottom, and here you have the unfinned area. If I use a different color, and in between you have the unfinned area. Okay, and then the last one is the area no fin. Okay. No fin means if there was no any fin, so these fins are not there, any of it. Okay, what was the heat transfer from the base alone? Okay. From this base alone, without any fins. Okay, we should find these 3 areas and calculate heat transfer. Firstly, let's write the values in Excel and then start calculating. First one is the number of fins. N fin is 6. Then you have P base, which is 230. You have the H, which is 25. You have, no, this is T infinity actually, and H is 60. Okay, now let's do it one by one. Firstly, the fin area. What is the area of the fin? Okay, so here again we'll use the chart. Firstly, before calculating the fin area, this one, you should see the chart here. So this chart is prepared for, see the corrected lengths. This one is assumes, this one assumes adiabatic tip. Okay, most of the charts are prepared assuming adiabatic tip. Therefore, we will assume that the area here is not the fin area, it is corrected fin area. Therefore, we should find the corrected fin area. Okay, let's calculate it. So we will add this corrected length, the radius, which is R2C. We should correct it, and then we will calculate the fin area. So let's calculate first the R2C in Excel. R1, first of all, let's write R1. R1 value is 25 millimeters, and R2 is millimeters, and R2C will be, R2C is R2 plus thickness. We have not written the thickness here. There should be thickness to thickness is how much? 6 millimeters, and R2C will be equal to R2 plus thickness by 2. So it's corrected length. Okay. Now let's calculate the fin area. Fin area will be, so you will have, this one is the cylinder. If you look at the top view, and around that cylinder you have the fin in cross section. Okay, you have fin here. The area of this fin is, this one is R1, this one is R2C. So this area is pi R2C square minus R1 square. This will be the area of the fin here. Okay, if you go back to here, you have area on top of it here, or you have the area here. Okay, you have another area which is below it, therefore you have two of it. You have one at the top and one at the bottom. So you should multiply it with 2. And you have also at the tip, this tip area plus area tip. And most of the time we neglect it because it is very small, and therefore we neglect it. Yeah, we will use this formula to calculate the area of the fin. Let's use it and calculate. So area of the fin will be 2 times pi times R2 square minus R1 square. It should be corrected as we have said. This is the area of the fin. Now let's calculated it, and then we should calculate unfinned area, the areas that we don't have any fin, and then area no fin. So let's calculate area unfinned areas. So this is the cylinder we have here. This is the cylinder. We have fins here. Okay. To calculate the unfinned area, we should subtract the total area from these thicknesses. Okay. So what it will be? So total area is this pi R1 into 2, so the circumference, okay, multiplied with this height into h. This is the total area, but we are trying to find the areas that are left in between the fins. Okay, here, these areas. What we will do then, pi R1 2, that is the same, h minus the number of these fins. So you have 1, you have 2, you have 3, you have 6 fins. Okay, it will be number of fins multiplied with the thickness. Okay, and then if you do that, you will calculate only the surface areas at these parts. Okay, let's do it. Area fin will be 2 into pi into R1 h. No, h is not here. Let's add the h value. Height was 0.15. And let's do it. 2 into pi into R1 into height minus number of fins multiplied with the thickness of each fin. Okay, which is the unfinished area. Now let's calculate the total area. Area no fin. Say area no fin is easiest part. We will calculate the area of the cylinder, which is, so you will calculate the area of the cylinder. You will have, this is the cylinder, but the area of the cylinder is 2 pi circumference 2 pi R1 multiplied with this height. Okay, do it. Will be 2 into pi into r1 h. Hi. Yeah, this is the northern area. Okay, so we have 3 areas, and now it is time to calculate the heat transfer from those areas. Okay, so firstly we should find the efficiency of the fin, because so the efficiency of, if you find the efficiency of the fin, eta fin, that will be Q dot actual divided by Q dot ideal. Okay, it's easy to calculate the ideal part. It is easier to calculate, to find the eta fin. This one will be from the chart, and this one, it is easy. We can calculate it, and then we will find the Q dot actual. Okay, so let's do that. So to find the eta fin, we'll use this coordinate, which is psi coordinate, and you have the corrected length to 3 by 2 and h k by ap. So this one is in brackets, and then you take the power 1 by 2. Okay, so let's calculate it, and then so psi will equal to firstly LC corrected length. Corrected length is L plus T by 2. This is the corrected length of this thing. So in our case, that is 50 minus 25. You will have this part, which is 25. So it will be R2 minus R1 plus thickness by 2. We'll have the thickness by 2. This will be the LC. And then if you find the LC, you can find this first, then you should find this AP, which is profile area. Profile area will be thickness into the corrected length. So A profile will be the corrected length into the thickness. Okay, we have all of the values, and now we can calculate the coordinate, which will be equal to this one to the power of 1 by 5 multiplied with h by, there's h by a value, conductivity of the fin. So we should add that to conductivity of the fin. The material is 20-20-46. Then we can use the book to find the conductivity of the fin. So this is the book that we are using. We will go to the appendix of the book. From the appendix, you will have the properties of the materials. We have the aluminum alloy, which has a conductivity of 177. Let's go back to here. So Ka of the aluminum is 177. Let's take the coordinate now. It will be Lc to the power of 1.5 multiplied with h by Kap. So you will have this h divided by, in brackets, the conductivity into profile area. So it's a profile area, and that one also to the power of 0.5. This one is 0.2. Okay, so it is very small value, 0.2, and for this value you have high efficiency. If you go back to here, 0.2. So you see all of the lines converge to that point. So it doesn't matter if R2C by 1 is 2, 3, 4, 5. All of the points converge to one. Lines converge to 1 point. Okay, it's approximately 0.95. Okay. You can also calculate this RT. For example, if you are here, you see one line, two. You have different lines. You should select one of them according to the problem. You should find R2C by R1. Okay. For our case, we don't need it, but you can find it. R2C by R1, it will be equal to corrected length divided by, and you can make it general, 2.12. So you see this line is our line. But anyway, it doesn't make any problem here. So efficiency is 0.95. Okay, this one is chart, using chart. The time is to calculate the Q dot actual. We know efficiency. Now we can find the Q dot ideal. Ideal is will be equal to the heat transfer from the ideal fin is equal to H into fin area. Now we'll use the corrected fin area multiplied with temperature difference, delta T. For our case, the temperature difference is 230 minus 25. H value is given. We have found these two values. Now let's calculate it. Q dot ideal fin. So it will be equal to, you will have the H value into the fin area and then the temperature difference. It will be T base minus T infinity. Okay. That means that from the fins we have heat transfer of 168 watts. So now we have unfinished parts, Q dot, unfinished parts. Unfinished parts, we have also heat transfer from these parts. We have heat transfer, but this one is only by convective CV heat transfer, and we don't need any efficiency, and that one will be also equal to area unfinished into again the same delta T. Okay, now Q dot unfinished will be again H into area unfinished into temperature difference, T base minus T infinity. It is 220 watts from unfinished parts, 168 from the finished parts. Therefore, Q dot total is sum of it. So 168 plus 220. This around 400 watts. So now we should calculate that if there was no any fin, what would be the heat transfer. So now the third option is what should be the heat transfer if there was no any fin. So that one will be equal to the base area. If there is no any fin, you will have the cylinder itself, and from the heat transfer from the cylinder itself will be the surface of the cylinder AS, we have found it, into H again into the same delta T. Let's find it. Q dot no fin will be equal to H again multiplied with area no fin multiplied with the delta T. So T base minus T infinity. Okay, so you have this amount of heat transfer. But this is with the fins and this is without the fins. Okay, you see you have 100 watt more heat transfer when we are using the fins. So if you increase the number of fins, let's make it 10. So this one is not affected. Okay, so the problem is this one is ideal fin. So I should, it should be real fin. So therefore this part is wrong. I should erase that part again. So Q dot ideal fin, so then it will be Q dot real fin. There are six fins, so I should include that one here. So because there are 6 fins and this one is for 1 fin, so then it will be equal to this one multiplied with efficiency. Okay, this one is for 1 fin and multiplied with number of fins, and this is the real fin. That is 962. Okay, it is good. So much. And then we will have the Q dot unfinished part. As we have said, it will be equal to H into area unfinished into delta T. T base minus T infinity. And the Q dot total will be this one plus that one. If you don't use anything, Q dot no fin, then you will have again the same calculation, H area no fin into the temperature difference, T base minus T infinity. We see we have a lot of heat transfer, 5 times, and without using, if you don't use any fin, it is 5 times less. So I can increase the number of fins. Let's see if it affects. No, it is okay, it affects. So we can make it as 15, we can make it as 50, 100. You see, temperature, the transferred heat increases. But after some value, you will see that, let's make it 10. So you will have a problem. What is the problem? The problem is that if you increase the number of fins, so let's say that you have a lot of fins here. So you have one fin, another fin, another fin, another fin. So lots of fins make a problem here because this gap for air travel decreases. Okay. As the gap for air to travel decreases, then you will not have a good heat transfer because then H value drops. Okay. Or H value drops because when air travels between these two fins, you have one fin here, you have another fin here. Okay. So air cannot travel in between in a good manner. Okay. It is not possible for the air now, and therefore the H value drops, and then you will not have good heat transfer. Then there should be no optimal number of fins. Okay, optimal number of fins. Okay, how do you guarantee that the number of fins are optimum? For that one, you should first set some thickness. Okay, you should set some thickness, and this should be the tolerance, and then you can add the number of fins, but keeping that thickness in place. Okay.